So far in this course, we've seen that there are a couple of kinds of different stationary points. We've got turning points because the graph is going up to a certain point and going down again, or going down and then going up again. And so the function is literally turning. So it's a turning point. Or we've seen that the function, although it doesn't change direction, in this case, this one's going up all the time, it does slow down to a stop. The gradient gets smaller and smaller. And then after it stops, it starts going up again. It starts getting bigger and bigger again. So that's called an inflection. So we've got turning points or inflections. Let's have a look at example 1. Example 1 says y equals 2x cubed plus 3x squared minus 12x minus 10. Yay. Has a stationary point. Nice. At negative 210. Oh. Determine if it is a local maximum, local minimum, or inflection. There's a couple of things I want you to take away from that. Number 1, you have not been asked to graph the function. Graphing the function, although it's really useful for getting a big picture of what's happening with the function, is not always necessary. Sometimes you just want to pick out critical pieces of information, like turning points, inflections, or x-intercepts or y-intercepts. You don't need the whole graph. You're just looking for a critical piece of information. Example 1 is exactly that. You're looking for, well, it says local maximum, local minimum, or inflection. It doesn't mention turning points. When you see the phrase local maximum or local minimum, it is referring to a turning point. A local maximum is a turning point where the graph is increasing before it and then, positive before it and then negative after it, or it's negative before it and positive after it from local minimum. The reason why it's called a local maximum is that, say for a cubic where it turns direction twice, technically this is not a maximum because the graph goes on forever beyond this blue line here, and therefore the maximum is infinite away. And similarly with a minimum. Even if we take a range of values from, say, here to here, this point here is a maximum of the function across that domain. That isn't. But it's a local maximum because it is definitely where the graph changes direction. Similarly here. Okay, so keeping that in mind, we have a local maximum, local minimum, and an inflection. And we want to be able to work that out without drawing the entire graph. You can see here I've got the solution started off, and I've started by working out the derivative. Now, I'm assuming by now you can use the power rule to work out the derivative of y equals 2x cubed, blah, 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 in a fairly straightforward fashion. So there we go. What you can see here also is that I've got this little table drawn out, and it's something to be done really quickly. And what we're going to do is we're going to use our understanding of what the derivative function does and how that relates to the original function in order to work out whether it's a local maximum, minimum, or an inflection. I've started the table off by having a gap either side of -2. Now, the reason why I've got -2 there is because at -2, we are told it is a stationary point. And that means that the gradient at that point is 0. In terms of the original function, it means that we have a point where the gradient has flattened out. So I'm going to put that down as a dash like that to say the gradient is flat at that point. Now what we're going to do is we're going to consider what's happening to the gradient either side of the stationary point. So I've got x equals -2, so I'm going to pick as easy as I can. I'm going to pick -3 to the left, and I'm going to pick, not -1, I think I'll pick 0 to the right of it, because they're going to be the most easiest values I can probably think of. What I'm interested in is whether the gradient is positive or negative after at those points. So picking -3, I'm going to have -3 squared here, multiplied by 6. So that's going to be -3 squared is 9, 6 is a 54. And then I'm then going to take 6 times -3 away, which is -18, and then take -12 away from that. So I've got 54 minus 18 minus 12. I don't care what that is. All I know is that that's definitely going to be positive. So I'm going to write a big plus there. Okay, what does that mean? If the gradient is positive at x equals -3, this is not this, but on the original function, positive looks like this. The graph is going upwards. So I'm going to notate that with a bar that's going up like that. Now at x equals 0, let's see what's happening here. At x equals 0, 6 times 0 squared is 0. 6 times 0 is 0, so they're gone, and I'm left with -12. So that means that the gradient at x equals 0 is negative. And what does that mean? A negative gradient means the graph is going left to right downwards. So I can use a little bar like that to show that it's going downwards. Okay, awesome, awesome, awesome. That means that without too much fuss, we can now conclude that I'll write that up properly again, that at negative 210, we have a local maximum. Done. It's a local maximum. So in other words, it's going up, flattening out, and down again. Up, flattening out, down again. So it must be a local maximum. If it was down, flattening out, and going up again, that would be a local minimum. So in slide 4 there, I know it's a bit pokey, so I apologize for that, but I wanted to fit it onto one slide. Here is our summary. So we've got a few notations here. So I'm saying I've got a point either side of a turning point here. The x coordinate of the turning point to be precise. So if f dash is positive, and then there's the turning point, and then f dash is negative. Sorry, I shouldn't put a dash there. And then the turning point will always be 0. And then we've got a negative here. Getting all my pencils right, there we go. Then we're going to have up, and then flat, and then down. So that's going to be a local maximum. That's what we had before. If instead I have it around the other way around, if I've got a negative and then a 0, then a positive, that's going to be down, flat, then up. That's going to be a local minimum. On the other hand, if I have a positive gradient, then a 0 gradient, then a positive gradient, that would be up and then flattens out and then keep going up. That's an inflection. And if I have a negative gradient and then 0 and then negative gradient again, that'd be down, flat, down again. It's another inflection. Okay, so if the gradient is the same sign either side of the stationary point must be an inflection. If it changes signs, then it's either going to be a local maximum or a local minimum. Refer to this table, but hopefully it makes sense. Let's have a look at a second example, and that will wrap up the video. I've made this up, so I have no idea what it's actually really like. But let's say this box has a volume of v of x equals 2x cubed minus 21x squared plus 60x. So we're able to adjust the value of x to get different volume measurements. And we're asked to find the value of x for which x is a maximum. So 6x squared minus 42x plus 60, straight power rule derivative there. And because I'm looking for a maximum, I know that I will find that at a stationary point. So I'm going to set that equal to 0, and then I'm going to work out what the nature of that stationary point is. First of all, I've got to solve it, I suppose. So I'm going to divide everything through by 6. I can do that now that I've set it equal to 0. So that's x squared minus 7x plus 10 is equal to 0. Then I'm going to work out what x is from that. I can see that this is fairly easily factorizable because minus 5 minus 2 is minus 7, and minus 5 times minus 2 is positive 10. So that's all good. And that means that x equals 5 and x equals 2. Okay, there are two stationary points, but we don't know which of those is a maximum and which of those is a minimum. Is it 5 or 2? Let's find out. I'm going to use my table again, like I showed you before, but my table is going to have more values in it. So I do my three rows, like so. And this is going to be x. Oops. This is going to be x. This is going to be my gradient, and this is going to be my function. And then I'm going to leave a gap between each of my stationary points. So here is a gap, and here is my first stationary point, which is 2. And then I'm going to leave a gap. And then I'm going to do my next stationary point, which is 5. And then I'm going to do one more gap. Okay, so a gap either side of my stationary points. Now, because I know that the graph doesn't change direction between 2 and 5, this is okay. I can just choose 1, 2, 3 values here, and I'll be able to work out what's going on. So what shall I choose? Easiest value before 2 has got to be 0, doesn't it? So I'll just draw in 0 here. Between 2 and 5, I can choose 3 or 4, so I guess I'll choose 3. And I can choose anything after 5, so I might as well just choose 6. So there's my values, and now I'll work out what's happening with the gradient. So first of all, I've got 0 gradient at 2 and a 0 gradient at 5. That's why I chose, that's why what I worked out before. So there's a flat there and there's a flat there. So that's filled in. Let's fill in the rest. So at x equal to 0, what have I got? I've got 2 times 0 is 0 minus 21 times 0 is 0. Sorry, I was looking at the wrong one there. I was looking at v of x. Let's look at v dash of x. 6 times 0 squared is 0, minus 42 times 0, which is 0, plus 60, so we've got a positive. So I'll pop positive in here, and that's an increase. Okay, this is telling me that I'm feeling pretty good. This is going to be my maximum. Up, flat, has to be down here though. If it's not, if it's like this, then I'll know it's an inflection. So I'll have a look at 3. So I'm going to put 3 in. 6 times 3 squared is 6 times. So I'm going to get my calculator out here. I think it's probably going to be easier. 6 times 3 squared. Oh, my calculator's being a bit slow. 6 times 3 squared is equal to 54 minus 42 times 42 times 3 minus 42 times 3, and I'm going to add 60, and I get negative 12. So that's going to be that's a negative gradient, which means that the function is going down at that point. So that's good to know. And then one last point is the 6. So I've got 6 times 6 squared. And then I'm going to take away 42 times 6. And then I'm going to add 60. And I get 24. So 24 is the value. So that's positive. And it means that the function is going upwards. So we can see from this that we've got this sort of thing happening here, kind of thing. And this must therefore be the local maximum. So we can conclude, i.e. maximum volume at x is equal to 2. Now, often you'll be asked things like, what is the volume? What is the maximum volume? And therefore you have to substitute 2 into v of x to work out what that maximum volume is. Or it might ask you for the dimensions because you've got other information which you can therefore use to work out the dimension. There's a few other variations, but as a very fundamental, here's a function, work out whether it's a local maximum or local minimum. This is exactly the process that you would use.